from Seoul National University in 1966, and he had his PhD in Purdue University in 1971, and he taught.
It is a real pleasure to be here. It turned out that today is a real beautiful day, and I found the campus to be also very beautiful. Let me first thank the organizer for giving me this opportunity, in particular Professor Chino Park. When I was asked to give a talk on organic devices, I wondered what this area means to chemical engineers. And it occurred to me that in the traditional silicon technology, as you know, the electrical engineers are the main players. But when it comes to organic devices, they kind of have a difficulty understanding chemical formula and chemical structure, and many times they just throw up their hands. And so I strongly feel that we chemical engineers can be the main players in this particular area. The way I understand, actually, in the industry where the efforts are being made, in fact, the major players are chemical engineers and chemists. It also gave me to reflect on what we did before, and it occurred to me that perhaps that our group is the first group to carry out a research project in Korea, probably industry included, in collaboration with Professors Chino Park and J.U. In what follows, I'm going to give a brief overview on each of these topics and then go right into some of our research results. When we talk about flexible display, of course we need flexible substrate. Shown here is the active matrix display made by plastic logic and e-ink. And of course, since it's flexible, you can bend it around. The issues related to flexible substrates are really the requirements that the substrate has to meet, and these are listed here. But the most important thing, foremost, is really the ability of the substrate to resist any permeation or diffusion of water and oxygen. The traditional approach for coping with this kind of problem was to use a multi-layer structure. And shown here is one example. That is, we have a silicon dioxide layer on polycarbonate. And in fact, this SiO2 layer is protecting the device, sort of, from the air and the moisture through this polycarbonate substrate. Another example is given here. What we have here is a metal TA deposited on a substrate. And as you can see, because of the difference in the thermal expansion coefficients, it bends. And of course, it can crack, that is, the metal surface cracks. But if you introduce an intermediate layer between TA metal and the polycarbonate film, you can see that the substrate does not bend, and you don't see any cracks occurring here. And of course, the reason is that you use a aluminum between the TA and PC, so that you can ease up the effect of the difference in the thermal expansion coefficients. Another example is given here. In this particular case, we have polyimide coated onto polycarbonate substrate. And of course, the role of polyimide layer is to act as water barrier. So, which brings us to the next part on patterning for fabrication of organic devices. And the issues here are, of course, foremost and first is the economics of fabrication. That is, whatever the process may be or whatever patterning technique you use, it has to be economical. And the one which, in a blunt way, the one which will cost you the least will win out. But in so doing, it has to maintain the device performance as well. And there's an issue on the resolution, that is how small a size you can go down to. So in this patterning, the conventional, I should say, the traditional approach is typically to use shadow mask. In this case, you have a shadow mask separated from the substrate by a certain distance, and through the opening you deposit the material of interest to you. And of course, because of this gap, you can have shadow effects, and it's very difficult to go down to below, say, 30 micron. Another approach is to use what is called cathode separator, and you make the cathode separator, shown here, through photolithographic means, and then you deposit the material in succession, for instance in OLED, to make the devices. So there's a question actually when we talk about patterning. That is why we cannot use the traditional or the conventional patterning of photolithography. And the reason is fairly simple, in the sense that the solvents used in the photolithography will degrade organic materials. And it's not suitable also for patterning organic films on flexible substrates because of the natural undulation of the substrates present, inherently present in the substrate. And as indicated, when we shadow mask, it is not suitable for a large area, and it's not also neither suitable for high resolution patterning. Whatever patterning we do, the directions we have to follow is to make sure that we have the large area patterning capability, also high resolution. It's got to be suitable for flexible substrates. When we talk about organic electronics, we often talk about OLED, that is organic light emitting diode, organic thin film transistor, lasers, and sensors. And as I indicated, large area applicability, the ability to go down to a small size, and foremost, of course, the cost effectiveness. Just looking back to what people have done to cope with this problem, we can go to Forrest Group at Princeton. He came up with what is called cold welding method. In this particular case, you have a stamp and you deposit the metal layer onto it. And also on the substrate, you have also a metal layer deposited. You press it, then you heat it up and remove the mold. And upon removing, of course, it takes the part in contact along with it. So you have the patterning done here. You turn around in about 2 years and see how this can be utilized in some other way. In this particular case, it's a sort of detachment. In this case, it's an attachment process. And people at Bell Lab, Lou is now at, I think, the University of Texas in Austin. And when she was there, the Bell Lab people came up with a similar method. In this particular case, you have a stamp and you deposit films that you want. But on top of any metal you have TI for, say, adhesion later on. And then you make the substrate get in contact with the stamp. You heat it up some, and then because of chemical bonding that is taking place between TI and the substrate, TiO2 to be more precise, you transfer the pattern from the substrate, from the mold to the substrate. Also, there were a number of efforts by Whiteside's group at Harvard. And in this particular case, he used PDMS mold or polydimethyl siloxane mold. And this perforated membrane is essentially act as a shadow mask, but in this time in contact mode, so you do the deposition and get what you want. They in turn turn around and see how you can do RGB, and in this particular case you have the same perforate membrane as before, but use another PDMS mode with the 9 openings. And you place this one onto that one, and that'll give you this kind of shape, that is the holes lined up along the line. In this particular case, you deposit R material, red material, and then you move this one, shift it a little bit to this direction and to the G deposition, and move it again, and then to blue deposition. That way, come up with this kind of RGB configuration. The Whiteside group also utilized their mimic, what they call mimic method, to pattern, in this particular case, penny, which is used as anode material. In this particular case, you have a PDMS mold placed on a substrate, place a drop of penny, and then the capillarity would suck this material into the channel, lift it up, and you can define this kind of anode material. The Forest group also did utilize their cold welding method in forming cathode this time around, and showed that indeed when you utilize this method, there's no difference between the transfer method and the conventional method as far as the device performance. And Rogers Group, this work was done not at the University of Illinois right now, but before he joined university, and was at Bell Lab. And in this particular case, you have a mold, and then you place the drops of PDMS, form a pattern mold, roll it and bind it around a cylinder, and then roll the cylinder so that the sand material here can be stamped onto this substrate. And then you carry out etching for electrode definition, to subsequent deposition for OLED fabrication. And this is called what is they call that reel-to-reel, sometimes roll-to-roll production. So let me then get on to what we do in this area. And before I do that, I'd like to introduce some unconventional lithographies that we have, named capillary force lithography, soft molding, room temperature, nano-imprint lithography, other techniques. The capillary force lithography, as the name implies, utilizes capillary force. And it's a fairly simple method to pattern anything. You have a pattern PDMS mold, as I talked to you about before, and place that onto a polymer layer spin-coated onto a substrate such as wafer. And then simply raise the temperature above the glass transition temperature of the polymer, which typically is around 100 to 110 degrees. And when the temperature is above TG, of course the polymer becomes fluidic, and because of the capillary force present in the void, the fluid material just fills up the void. You just cool it down to room temperature, remove the mold, and there you have the pattern formed. So in this case, there are two different cases. That is, either you have residual layer when you have thick film to start with. If you have a thin film to start with, then the substrate surface is exposed. And examples are given here, the result of CFL. And as you can see, the fidelity of the pattern form is pretty good. In this case for thick, and in this case for thin. These results were obtained about 4 or 5 years ago. Although the time says about 24 hours, it can be done these days in less than 10 seconds. In a similar way, in soft molding, we use capillarity in the same way. You except that the capillarity is induced by the fluidity afforded by the presence of solvent. That is, in this case, you have a substrate, say a wafer, and then you use any polymer, you just spin coat it, and then in wet state you place the mold down, and then the vapor, solvent vapor just diffuses out through, and then after a while you get this kind of pattern form. So this one here is fairly simple. You do you just spin coat and then just in a wet state you place the stamp down, and then after a while you get the form. And the examples of the comparison between original master pattern and the pattern formed by soft molding, you can see they are almost the same. We also have room temperature nanoimprint lithography. In this particular case, the principle is rather simple. You have a polymer layer, you place the hard mold down, and in brute force you press it down and remove it. The nano imprint lithography was originally developed by Steve Cho at Princeton, and he uses very high temperature, but in this case we utilize plastic deformation polymer, and so you can carry it out at room temperature. It gives some unique capabilities that hot process wouldn't. Shown here are some mixtures of patterns, including some pattern in the sub 100 nanometer. So with this introduction, let me go in right into the cathode patterning, nanoscale OLEDs, and patterning OLEDs, also by simple detachment method. Next. One of the methods that we utilize is to do metal transfer. In this case, you have a glass mold, and you put on a SAM or a self-assembled monolayer to help release of this aluminum later on. And you just put it down onto the organic layer, press it, and release it, and you get this metal lines form. So it's a simple transfer technique. And shown here is the simple passive matrix OLEDs, and these black ones are the aluminum lines formed. The faint in the background here is the ITO electrodes, and so you can have this passive matrix through this metal transfer. Whenever you use an unconventional method to fabricate any device, the question is whether that is going to affect any device performance. So here's a comparison between the device formed by the conventional method, in this case shadow mask, and our method. In the very low current range, there's an anomaly here, but in the operating range, you can see there's not much difference between these two methods. And also the same is true with the EL spectrum. And at the outset, I talked to you about the use of cathode separator, and I also indicated that the separator is usually fabricated by conventional photolithography. We thought that we could utilize our technique to make this kind of inverted tropozoid type of shape. And so what we do in this case is utilize this kind of master, make the mold out of it, and then you utilize mimic, and then remove the mold, and thereby generating the same pattern as this one. So here's a typical example, or the actual results. This is the master. This is the mold made from this master. The cathode separator made with the use of this master. Now, upon magnifying the edge of this cathode separator, you can see that there's enough clearance between this edge and that to give you good separation between adjacent devices. And in this case, we also did make passive matrix, and we just turned on by applying bias this way and 3 lines here, turned on 3 pixels. And in this case also, we see that not much difference between our method and the usual method. Another question we had along the way was to see whether a small device would function just like a big device. In this case, we made actually by patterning this polystyrene layer in this here, acting as a barrier here and forming 80 nanometer device in this gap. And actually we found that there's this 80 nanometer scale device, as shown later, would function exactly a big device for it, but we found some shift in the EL spectrum, and this is probably due to scattering taking place along the zigzag type patterning done. Now shown here is another unconventional method we developed. We call that simple detachment because it's fairly simple. You have a glass substrate, of course, for OLED fabrication, and you put on the organic layers that you want. You place the stamp down, and then raise the temperature to below glass transition temperature, in this case typically below 90 degrees. We don't do anything, do not apply anything at all, pressure that is, and just simply remove the mold, and the part that was in contact with the protruding part of the mold gets lifted. So simple detachment. So to show that it is effective, we did some actual patterning here. We had MPB layer on ITO coated glass, MPB being the whole transport layer. And we could see that the patterning can be done fairly well. And also we wanted to show that the method is equally effective when you have a series of lines with different size, in this case from 1 micron to 70 micron size. And we also wanted to see the edge fidelity, and you can see the fidelity is not that bad. And in this particular case, another example of the patterning done through the simple detachment method. Shown here is the 600 nanometer lines. Of course, these kind of lines cannot be defined by the shadow mask technique. So when we do that, we also wanted to show that it works with the device as well. That is, when we apply that technique to fabricate the device that results would work properly. And in this particular case, in this part, the NPBs, in this case, we use ALQ3 active layer, and ALQ3 is missing here, so no emission. And so you can see green emission, also line pattern, light emitting through line patterns. This here is the sort of grid structure. But if you do not do a good job of detachment, there's some residual layer remaining, and so you have a smearing effect. And here also what we tried to do was to show that actually it really doesn't make any difference whether you do the fabrication through our simple detachment method or the conventional method. And you can see that they are more or less similar in terms of IV characteristics as well as luminance and current density. Which brings me to the last subject, which is device performance. And the issues here, of course, always is mobility, because in organic devices, the mobility is very low compared to silicon devices. And when you use organic substance, there's always a shift in threshold voltage, and so there's a need to control this one. Another concern has to do with the on-off ratio, which tends to be very low compared to silicon devices. And there's an issue about the channel length, which in a way determines the device characteristics as well as the number of devices you can jam into a given area. And of course, there's always this, when it comes to organic material lifetime issues, which are related to materials, encapsulation. Let me just go into a brief review of active materials and gate dielectric materials. And as far as active material, organic semiconductors, typically small molecules are used. The preferred substance is Panasonic these days. It will give you good crystallinity, and through vacuum deposition you do the formation. Polymer semiconductors, conjugate polymers is used. Of course, because of nature of polymer, crystallinity is not that great, but it does give you the advantage of being able to do solution processing, which is cheap. And this particular one I mentioned briefly, so let me just move on to semiconductor next one. So let's go back to field effect mobilities about organic semiconductors. It turns out that when they tried in 1988, the mobility was 10 to the minus 3 square centimeter per volt per sec. And in about 15 years, about 4 orders of magnitude improvement in the mobility. These days, Panasonic about 5, it says. But if you are careful and willing to spend time, the mobility can go up to tens of square centimeter per volt per sec. So the key to what, can we go back? Key to what is shown here is that in terms of mobility, organic transistor is comparable to amorphous silicon, and probably this is the key. But when it comes to polymer semiconductors, that is not the monomolecular organic, but rather polymer, the performance gets fairly bad. 86, 10 to the minus 5. Although there has been an improvement of the order of, say, about 4 orders of magnitude, still about an order of magnitude smaller than organic, the Panasonic, for instance. So the inorganic semiconductors, the issues for better mobility, shall we say, is really the molecular structure. That is, the molecules are relatively well ordered. You go from this low mobility to bigger mobility. And the same is true with Panasonic. As I indicated before, Panasonic will give you crystalline structure. Shown here is more or less the grain of the Panasonic molecule. And as you can see, as you increase the temperature, for instance in this case from room temperature to about 100 degrees, you see a vast improvement in grain size, which in turn means higher mobility. Also shown here is the effect of molecular structure in the case of polymeric material. And it has really to do with the regularity of the molecule. And for instance, if it's aligned this way, and the pi bond here overlaps with that one, there's a natural conduction path here so that electrons can flow fairly well this way. But if it's stacked this way, the overlap is in this direction and the electrons travel this way so that you eventually have a lower mobility. And with the polymer semiconductor, the highest mobility is in the range of about, as indicated before, 0.02. So let's move on to then gate dielectric materials. In the same way as the silicon people do, inorganic insulators have been used. But of course, if you have flexible display, you just can't use this kind of thing, although there's an effort by John Rogers' group these days to utilize this one even for flexible substrate. Organic insulators, typically polymers, and that gives you flexibility, but the weak point here is that it can be degraded by solvents. And one example here is to how the grain size of panasin deposited on SiO2 can be changed. That is, by depositing, by treating the surface with the sand material or self-assembled material, the grain size, although not that well shown here, the grain size and the electrode as well as in the insulator, they are the same, whereas when not treated, they are different. In the case of polymer used as gate insulator, as you can see, as I indicated before, it's still around in the range between 10 to the minus 1 and 10 to the minus 2. So which brings us to our efforts in this area. One of the things that we tried to accomplish was to see how we can eliminate the shift in the threshold voltage or hysteresis. And shown here is a typical ID curve you get when you do the bias scan from reverse to forward. That is, you can see there's a hysteresis. And if you have this kind of device, you just can't use it for any practical purpose. So this has to be eliminated. The same is shown here for this capacitance versus voltage. In the literature, there are a lot of reasons given for this hysteresis behavior. That is, what the origin of this hysteresis is. But the fact of the matter is that whenever we have this dielectric material thickness increase, the hysteresis also increases, which in turn indicates that perhaps this matter has to do with the bulk characteristics rather than the typical interface or surface characteristics. So what we did was to use, as shown in the previous slide, we use a double layer that is bilayer, that is a polyvinyl phenol, very thin one, and a very thick polyvinyl acetate film to eliminate the hysteresis problem. And as you can see, when we use a PVPH as the gate dielectric, you get high mobility, but you do have this undesired hysteresis problem. As you can see, mobility is about 0.1. Whereas you do not have any hysteresis at all, but the mobility is fairly low, typical value. But when you have the kind of bilayer that I talked to you, you can combine this high mobility with the no hysteresis, such that you get a no hysteresis with the bilayer, which means no threshold voltage shift, and you can have satisfactory mobility as well. And the reason has a whole lot to do with the grain size on a given insulator. That is, on the PVHC, the panasin grain size is fairly small, as you can see here. On the PVPH, grain size is larger. In the bilayer, the same kind of grain size. In another effort, we tried to come up with I shouldn't say new, but let me just say new gate dielectric material. It's known in the literature that with the inorganic dielectrics, such as silicon dioxide, and using polymer semiconductor instead of panasin, mobility is around 0.2. If you use of course, use a panasin and then polymer gate dielectric, the order is of the order of 1. Next one. So what we did was to come up with this PHEMA and utilize this PHEMA as the gate dielectric with the diode type P3HT active layer. And we carry out the formation of the active layer through different coating methods, spin coating and drop casting, and also utilize various different kinds of solvents And note that the solvent used for coating PHEMA is methanol, whereas the solvent for coating P3HT is organics, that is, for instance, toluene. And you can see that when you do the toluene drop casting, you can get highest mobility ever reported in the literature. That is, with the polymer gate dielectric and polymer semiconductor, this is perhaps the highest mobility ever reported. However, as you can see, as is typical with the polymer dielectric and polymer semiconductor, the on-off ratio is fairly low. The comparison between drop casting and spin coating: when you do the drop casting, evaporation takes place fairly slow, which gives enough time, or relatively enough time, for slow growth of the polymer film, which results in better ordering of the polymer, in turn gives you better device performance. And as I will be going in some detail, it turns out that surface roughness is a key factor and is indeed induced by solvents. Although you use compatible solvents, and because of these poor ordering and solvent effects, you have poor device performance. Shown here is the roughness of the surface when you have no solvent. It is fairly flat, relatively speaking. When you use toluene, a little bit more, but if you go to bad solvent, that is bad for the device, you see a whole lot of roughness here. It turns out that the mobility decreases when we tested all these, that the mobility decreases with increasing surface roughness. So the parameter that can characterize this the solubility is, of course, the solubility parameter. And in short, one has to use a solvent with the solubility parameter that is furthest away from the dielectric material you try to form for best device performance. And the last one, I'll just move on, utilizes dry transfer. In this case, you transfer the active polymer semiconductor layer onto the underlying dielectric. And as a result of this, because by doing the dry transfer, you eliminate the bad effect of solvents. And you can do also, if you want to, before transfer, you can add the surface, you can make the surface hydrophobic. And also, if you like, you can do annealing as well. And so as you can see that when you use this one here, I think is PHEMA is gate dielectric compared to with the direct transfer method and the solution technique. You see a huge difference in the device performance. The same is true with the PVP gate dielectric. As I indicated, with the dry transfer method, you can do heat treatment, which results in improvement on-off ratio. That is, when you do the spin coating, the on-off ratio is about 100, about 1,000. So you get some improvement in on and off ratio by heat treatment prior to the transfer. And because you do not use solvents, you do not generate the defects and voids. You can allow better ordering if given sufficient time, which in turn leads to better device performance. So let me summarize here my talk. I gave an overview and then move on to device fabrication, to talk about metal transfer, simple cathode separator, nanoscale OLED, and simple detachment technique. And also I talked to you about the device performance as affected with the cooperative dielectrics and a new polymer gate dielectric and the method of dry transfer of active layer. So just wrapping up, what does it mean to us? What does the future hold? I ask myself, and I can foresee, and I can, in a sense, I can say predict that we'll have commercial flat panel organic display, not with the organic TFTs, but silicon TFTs, in about 2 or 3 years. It's just like what TFT LCD was in 1992, around there. And if you recall, the TFT LCD business took off in 3 years, around 1995 and 96. I believe the same will happen. After that, or concurrent with that, we'll have flexible or organic display. And finally, we'll have all organic flat panel display. Thank you for listening.